Hello, so today we're going to be doing a few tasks. So in task number 1, we are going to be going over some example of a strong base and a good nucleophile. So this, I will be drawing here an example of a strong base. Here I am just writing it out. There. So this will be one of our examples of a really good strong base. Why might you ask? Well, let me draw it a different way so you can better visualize it. So we can think of potassium here as a kind of like a spectator ion. So potassium bears that positive charge while oxygen bears a negative charge. And can't forget those lone pairs. It will fully dissociate in solution, producing OH ions. And while it bears that negative charge, this indicates a really strong base. Perfect. Here I am just writing out that the hydroxide ions would form in this case scenario. Factors that make species strongly basic also contribute to actually nucleophilicity. And here, let's draw now, since I mentioned this, let's draw a good nucleophile. So here it is. Let's just do sodium and then sulfur H. Okay. In this case, let me redraw it again so you can definitely see. So think of sodium as a spectator ion in this case. It bears that positive charge while sulfur bears a negative charge. Notice they both bear a negative charge. This is the good nucleophile portion. Since S is bigger and it is bulkier, it makes it a better nucleophile rather than a base. This actually goes off. We can look at trends of the periodic table, but in this case, we'll stick with the fact that it's a good nucleophile. Strong nucleophiles will often bear a negative charge. If we compare, for example, sulfur, neutral sulfur, and sulfur with the negative, sulfur with the negative is a lot better. It's a better nucleophile. Okay, now let's compare. What is going to be in common between these two? We might have heard me say it. Well, they both bear that negative charge. Both a base and a nucleophile are electron rich. They have lots of electrons, and they want to give it up. So this negative charge that they have with lone pairs of electrons, they can donate said electrons. They want to. A strong base and a good nucleophile are extremely high in density, extremely high in electron density. Here I am just going to show you what I mean by that. As you can see when I draw it, there are those pairs of electrons, lone pairs, very high in electron density. That's exactly what I mean by that. Okay, so let's go over some differences between the two. Well, first and foremost, bases like to take protons, while nucleophiles will be attacking a carbon where a leaving group is present. In our case, in our examples, where carbon is the one that gets attacked. Nucleophiles attack any electron poor atom. In this case, for us, it is carbon at the moment. We also have a thing called steric hindrance. If we have a big and bulky species that is also hindered, it can be a strong base, but not necessarily a good nucleophile. Electronegative atoms hold electrons close and they hog electrons. They don't share as readily as less electronegative atoms. So in this case, if we were to compare something like methyl and hydroxide, that methyl is going to be a lot better. In this right here, I'm just writing down that sulfur is our bigger and bulkier, and it's better as a nucleophile, and it's polarizable. Good nucleophiles will always be polarizable, meaning they have delocalization of electrons. So here I'm just going to draw a few trends to kind of help visualize this a little better, what I mean. So here I'm just going to draw a box, pretend it's your PT, or periodic table. So going from right to left, our basicity and nucleophility will increase. This is very important. You don't always have to go based off this, but it's a little good thing to kind of look at. And then if we go up the periodic table, if we were to go from iodine to fluorine, basicity increases going up. So going from the bottom up to the top. While if we go down, nucleophility increases going down. I'll show a quick little example of what I mean by this. So here I'm just going to draw a small column. Oh, let me draw that again. Oh, okay. So let me split this up into 4. So we're going to go fluorine, chlorine, bromine, and then iodine. So our weakest nucleophile, our most electronegative nucleophile is fluorine. This is going to be a weak nucleophile, but it goes opposite. It would be a very strong base. Iodine is going to be our strongest nucleophile, least electronegative, weakest base. This, what I meant by polarizability, is atomic size increases. So the bigger we have in the atom, it's going to be a better nucleophile. It's polarizable. Its electrons are delocalized. There's more space. Like I said before, our electronegative atoms hold electrons close together. They don't want to give these up. In a head-to-head comparison, if the electrons are delocalized by resonance, then the species is going to be less able to donate electrons in this case scenario. Okay, so that was these 2 examples and the pure differences of the 2. So now, let's go to task 2. Let me just erase this so we have some space for task number 2. In this task, we're going to be determining what mechanism and drawing it out. Okay, so let's get to it. So first we want to start off with classifying our substrate. So here's our chiral center. There it is. And then let's determine the substrate. Let's classify. So this will be secondary. Why? Well, around that carbon center, there is 2 other carbons off to the side, making it secondary. And it is also resonance stabilized. I will show that a little bit later, but it is resonance stabilized. So this right here is our solvent, but we can compare it as nucleophile base. In this case, it's a nucleophile, but it would be weak no matter what. This is a weak nucleophile or weak base because 2-propanol can be considered as both. It can either be weak base, weak nucleophile. Okay. And as you can see, no heat is involved. It is not portrayed under the arrow, so therefore we can easily eliminate E1 and E2. And the fact that this is resonance stabilized and secondary, it cannot be SN2 as well. And then here I'm just showing you that this is neutral, which is indicating why it's not a really good nucleophile. Okay. That's me just writing down that it can be both. But because it's SN1, we'll treat it as a nucleophile. There it is. So this is SN1 here, and then here I am showing you where that resonance stabilization is. It's wherever there's a double bond close to where that leaving group carbon is. Leaving group. And then here's that other double bond right here, also sense of resonance stabilization, indicating SN1. Because a carbocation can form in multiple places. Okay, let me draw some products. So these will be our expected products. So because it's SN1, I'm going to make sure that we can either draw planar but in this case, it's going to be a pair of enantiomers. So the first one, this will be, sorry for the bad drawing, not really straight, but it's okay. Remember, SN1, our solvent or nucleophile, if we want to treat it as a weak nucleophile in this case, it will take place of where that chlorine is, our leaving group, so it left, and then I'm going to draw that other pair, second pair of enantiomers, first pair is just the other way to draw it. And then it's going to be going away from us with the oxygen. There we go. And then if we really want to draw those lone pairs in to really show that that's how it should look. So this is a racemic 0% EE. So now we can't forget that our solvent, it will gain a proton. This will be showed via mechanism, which I'll show just in a little bit. So here we go. Here's our leaving group of chlorine. Here's its lone pairs. It's negative. And then we have our 2-propanol gained a proton. So that oxygen is now, it gained the plus charge. This is, again, expected products. Perfect. Now let's draw the mechanism for this thing. So this is going to become planar. Cl gets pushed down. So planarity. So as we draw this, I'm just going to redraw that structure, but I'm going to show with a red arrow instead so you can really see what I mean by chlorine leaves. This is our leaving group. Let me just get my red pen out. Perfect. Chlorine leaves. So when we draw this, a carbocation forms. There we go. Boom. Can't forget that double bond in the end. There we go. And then this is indicating like a hydrogen, but it left. So our carbocation has officially formed. Here's our Cl. Here I'm going to redraw it again so you can see how our solvent now is going to, or nucleophile in this case, is going to attack that carbon because it wants electrons. It's in need of them. And her nucleophile is electron rich. Boom. Okay. Now, oxygen is going to take place. Let me just redraw it. There we go. Double bond. Then we're going to draw that bond and then oxygen. And then the other part of it, nucleophile. But remember, our hydrogen has not left yet. And oxygen still has that. It now has a positive charge because that hydrogen joined along with it. We still have that nucleophile. So now our solvent, it comes back again. We are undergoing solvolysis in this case. Remember, lone pairs, let's draw that. Let me draw a hydrogen actually on the other side so you can see what I mean, what's going to happen. So because we're undergoing our solvolysis, our solvent is going to gain a proton. So hydrogen gives that pair or that bond, it gives it another lone pair. This lone pair on our solvent takes that proton away. Now we get this product. This is actually our final stage. Let me just draw the ring, put some double bonds in. There we go, another double bond. And then here, because oxygen gained another pair of the lone pairs, it lost that proton. And then let me just draw in our solvent now that it gained the proton, H2, plus it's a positive charge now. Can't remember that other part of it. And then chlorine, our leaving group. And there you have it. That is our answer. This is what we get. Another thing I forgot to mention for nucleophiles and bases, nucleophiles are electron donors. They have a delta positive, while bases are electron donors as well, but they take that H plus. Or nucleophiles, they attack something that has a delta plus, like our carbon. And yeah, there we go. And then the reason why this is, it's actually here I am just labeling that it's racemic 0% EE. It's a pair of enantiomers. There we go, just showing you what I mean by this. There's that percent EE, 0% EE. And then, if we really want to go into further detail, I'm going to go over why in the world this is SN1. If I compare SN1 and E1, we have weak nucleophiles and weak bases. And then we also have product solvents, and the two can undergo solvolysis. So when doing this, I'm going to show you how I eliminated E1. So if we look at this, our solvent, in this case, it's weak nucleophile, it can be a weak base. It is product because a part of the list of what can be product, it's an OH group with an R group attached to it. This is solvolysis. It's a solvent. It's going to undergo solvolysis for our thing. And there we go. This is our answers to our problem. Yeah, here I'm just saying that weak nuke. And there we go.